Welcome to Organic Chemistry. Today we are going to explore one of the most fascinating decision-making processes in chemistry, Saytzeff and Hoffmann eliminations. Imagine a molecule as a crowded city, and we need to build a new double bond. Do we bulldoze through the center or take the easy route on the outskirts? Let us find out. To begin our journey, we must first understand what an elimination reaction actually is. Why does this matter? Because elimination reactions are fundamental tools chemists use to synthesize complex molecules, like life-saving pharmaceuticals. In this process, a molecule loses atoms to form a new carbon-carbon double bond, transforming into an alkene. A chemical called a base acts like a thief, stealing a proton from a carbon atom. Simultaneously, a leaving group departs from the neighboring carbon. The two carbons, now missing atoms, share their leftover electrons to create that double bond. Now that we know what an elimination reaction is, we face a problem. If the starting molecule is unsymmetrical, the base has a choice of different hydrogen atoms to steal. This is where our two main rules come in. The Saytzeff rule predicts that the major product will be the most highly substituted alkene. This means the double bond is placed in the middle, surrounded by the maximum number of carbon groups, making it highly stable. On the other hand, the Hoffmann rule states the exact opposite. It predicts that double bond will form at the very end of the chain, creating the least substituted alkene. Before we can predict which rule wins, we must introduce a mandatory physical requirement called stereoelectronic control. Why is this so crucial? Because molecules are not flat drawings on a page. They exist in three-dimensional space. Stereoelectronic control dictates that a reaction can only happen if the reacting atoms are aligned perfectly so their electron clouds can overlap. Specifically, elimination requires an anti-periplanar geometry. This means the hydrogen atom being stolen and the leaving group departing must lie in the exact same flat plane but point in completely opposite directions. If they do not align, the reaction simply will not happen. Let us visualize this strict requirement with a diagram. Here, you're looking at a Newman projection showing the anti-periplanar geometry. Notice the central circle representing the carbon-carbon bond axis. The leaving group, labeled X, points straight down. Exactly opposite to it, pointing straight up, is the hydrogen atom, labeled H. The red arrows show the base attacking the hydrogen and the electrons flowing down to kick out the leaving group. The 180-degree angle between them is the critical feature. This perfect opposite alignment is what allows the electron clouds to flow smoothly and form the new double bond. With the 3D geometry in mind, let us look at our first pathway. When stereoelectronic control allows for multiple choices, the Saytzeff rule usually dominates if we use a small, nimble base like sodium ethoxide. Because the base is small, it can easily navigate into the crowded middle of the carbon chain to reach an inner hydrogen. Since reaching the hydrogen is easy, the reaction is driven entirely by the stability of the final product. The resulting highly substituted alkene is stabilized by hyperconjugation, where adjacent bonds act like supportive pillars. This is the default, most common pathway. But what happens when things get crowded? The Hoffmann rule takes over when we encounter steric hindrance, which is simply physical crowding between large groups of atoms. If we use a massive, bulky base like potassium tert butoxide, it is simply too fat to squeeze into the middle of the carbon chain. It bumps into surrounding atoms and bounces off. Frustrated by this crowding, the bulky base takes the easiest path available. It grabs a hydrogen from the completely exposed, uncrowded end of the chain. This forms the least substituted alkene, known as the Hoffmann product. To truly understand this competition, we turn to physical chemistry and the Arrhenius equation. Conceptually, this formula calculates the speed of a chemical reaction based on the energy barrier it must overcome. Let us break down the symbols. K represents the rate constant, or how fast the reaction goes. A is the frequency factor, representing how often molecules collide. EA is the activation energy, measured in joules per mole, which is the energy hill the molecules must climb. R is the universal gas constant, and T is the temperature in Kelvin. When a bulky base is used, the physical crowding causes the activation energy for the Saytzeff path to skyrocket. Because EA is in the negative exponent, this massive increase causes the rate K for the Saytzeff path to drop to almost zero, allowing the Hoffmann path to win. Let us apply this knowledge to a real molecule and predict the major product. We are given a 4-carbon chain called 2-bromobutane, which has a bromine atom acting as the leaving group on the second carbon. We need to determine where the double bond will form when we react it with different bases. Our first step is to identify the neighboring carbons that have hydrogen atoms available to be stolen. The bromine is on carbon 2. Therefore, its immediate neighbors are carbon 1, which is at the exposed edge, and carbon 3, which is buried in the middle. First, let us see what happens with a small base. In this scenario, we use ethoxide, which is small and unhindered. Because it is small, it easily bypasses any minor crowding and reaches the hydrogen on the inner carbon 3. We remove this inner hydrogen and the bromine, forming a double bond in the middle of the chain. This gives us 2-butene. This is a di-substituted alkene, meaning it has 2 carbon groups attached to the double bond, making it highly stable. Therefore, with a small base, the Saytzeff product is the major result. Now, let us swap that small base for a massive one. We use tert butoxide, which is a very bulky base. Due to severe steric hindrance, this fat base cannot squeeze in to reach the hydrogen on carbon 3. Instead, it takes the easy route and plucks a hydrogen from the exposed carbon 1 at the edge. This forms 1-butene, a mono-substituted alkene. Even though it is less stable, it forms much faster because of the crowding. This gives us our final answer. The bulky base forces the Hoffmann product to be the major result. We have seen the standard rules, but sometimes molecules break our expectations completely. Let us look at a real-world challenge that proves why stereoelectronic control is the ultimate boss. We have a molecule called methyl chloride, which is a 6-membered carbon ring with a chlorine leaving group. Surprisingly, even when we use a small base, methyl chloride produces 100% of the less stable Hoffmann product. The highly stable Saytzeff product does not form at all. To understand why this happens, we must ignore the size of the base and look purely at the 3D geometry of the ring. To solve this mystery, we must return to our strict 3D requirement. Conceptually, this equation defines the exact spatial relationship required for an elimination reaction to occur. The symbol theta represents the dihedral angle between the leaving group and the hydrogen atom being removed, measured in degrees. For the electron clouds to overlap and push the leaving group out, this angle must be exactly 180 degrees. This means they must be perfectly anti-periplanar. If this angle deviates significantly, the orbital overlap fails and the reaction cannot proceed, no matter how stable the final product might be. Let us analyze the 3D structure of methyl chloride using the strict angle requirement. We are looking at a cyclohexane ring. In this specific 3D conformation, the chlorine atom, our leaving group, is pointing straight down in what we call an axial position. To satisfy the 180-degree dihedral angle rule, the base must remove a hydrogen atom that is pointing straight up, also in an axial position, on an adjacent carbon. This is the only way they will be perfectly opposite to each other. We first look at the more substituted neighbor to see if we can form the stable Saytzeff product. We check the adjacent carbon that has more carbon groups attached. However, when we look at the atom pointing straight up on that specific carbon, we find a giant isopropyl carbon group, not a hydrogen. The hydrogen on that carbon is pointing out to the side at the completely wrong angle. Because the required hydrogen is not perfectly opposite to the chlorine, the base cannot push the electrons in. Therefore, the rate of forming the Saytzeff product, Ks, is exactly 0. Since the Saytzeff path is blocked, the molecule has only one choice left. We look at the other side of the chlorine, at the less substituted carbon. Here, we find a hydrogen atom that is indeed pointing straight up in the axial position. Because this is the only hydrogen in the entire molecule that satisfies the 180-degree anti-periplanar rule, the base has absolutely no choice but to take it. This forces the molecule to form the less stable alkene at the edge of the ring. Our final answer is that stereoelectronic control forces 100% yield of the Hoffmann product, YH. As we wrap up our discussion, let us review the key takeaways. First, the Saytzeff rule favors the most stable, highly substituted alkene and is the default pathway for small bases. Second, the Hoffmann rule favors the least substituted alkene, taking over when bulky bases or leaving groups cause physical crowding. Finally, stereoelectronic control is the ultimate boss. The strict requirement for a 180-degree anti-periplanar alignment can completely override all other preferences. You now have the steering wheel to drive these chemical reactions exactly where you want them to go.